There's nothing like being bright and alert to handle some of this material.
Yeah.
I mean, I hate, to be honest with you, I hate 9 p.m. sessions on calculus because my brain is tired by then. So, um, so what are we doing today? We must be doing double angles and half angles and solving trig equations.
Well, like, because we did verifying last week a little bit,
Uh-huh.
so it's like more verifying, but we started going into like multiple choice verifying, so it's gotten like a little trickier.
you you bring up an excellent point.
Yeah.
If a teacher wants to be
Who's my teacher?
the worst possible teacher, give multiple choice trig verifying questions. And
Yeah.
I don't mean the worst teacher. I mean if he wants to
No.
torture you the most.
Yeah, I know.
It's
Uh-huh.
it's the only questions I can think of where multiple choice makes it harder.
It
Uh,
does. Yeah, definitely.
and the reason is this, is that all of the trig verifying you've done prior to the multiple choice were all identities. Okay?
Exactly. Yeah.
The only thing you learned how to do was to prove an identity. They haven't taught you how to disprove an identity.
I know.
And when you have multiple choices, you kind of have to do that. I guess. Can you send me a picture of some of these? So
Yeah. So how do I do
I read
that?
them all verbally.
So do I like take a picture and send it to your number?
Send it to my email address, which I'm writing on here. And then this will be stored in your phone and it'll be easy to do the next time you do it.
Okay, perfect. So should I take a picture of like each one individually or like a picture of the whole sheet?
The whole sheet is fine.
Okay.
Uh, try not to put more than one attachment with one email. If you put multiple attachments, it takes a while to get to me. Whereas if you just
Okay.
put one picture, we can work on that, and if you have more to do, you can send them afterwards. Um,
Okay.
but
Wait.
make sure you spell this correctly, because are you using an iPhone or a Samsung
Yeah.
iPhone?
It's a,
If it's an iPhone, make sure you send the image as a large image, not a small image.
okay.
Small images, by the time I blow them up on my screen, we can't really read them. But if you take a large image, it comes out very high resolution.
Large image. Gotcha. Okay.
I had an iPhone student the other day that she was not getting that question, large or small. And I guess the way she was doing it, she was taking a picture and then texting it to my email address. And that was problematic, and I'm not quite sure. I guess it eventually got to me, but it took a little bit.
Okay. I sent it. It's large.
I don't have an Apple iPhone, so it's hard for me to tutor you on how to do it. I know how to
Yeah.
do it
Okay.
with my Samsung for sure. I just pull up the picture on my gallery and then I say share, and I use the Gmail option to share it. So let me know when you sent it.
Okay. I sent it, so
Okay.
should be there soon.
Yeah, it'll take a few seconds. Let me line this thing up. Yeah, it looks like maybe it just came in. You sure you sent it to this email address? With the 1940?
Wait. Let me check 1 sec.
Okay.
Yeah, David Cohen 1949 at gmail.com.
Yes. And it's
Okay.
Cowan, C-O-W-A-N,
Yes.
I had a student misspell it once and put E in, and then he typed it next time he did it correctly, but then whenever he typed the first two letters, both of them came up, and he didn't know which one it was correct, so I got it.
Oh, did you get it? Okay.
Looks like I got to download it so that I can rotate it. Yeah, this works pretty good. It's pretty easy.
Okay.
Gonna need what? 3? Yeah. All right. Let me blow it up a little bit. Where do you want to start? The top?
Just with number 1, yeah.
Okay. Well, let's see. Sometimes it feels to me like one is almost better off just attempting to manipulate this thing, but let's have a look at what they want us to change it into. This one's got a cosine and a tangent, which is sine over cosine. This got sine over cosine. This got cosecant, secant, which I could put in terms of sine and cosine. This one's got cosine. So I would say the way to handle this is to convert everything to sines and cosines and see which one.
Okay.
Okay. So
what's
the first thing?
You
Let me
change.
blow it up. Yeah, go ahead.
Okay. You change cosecant into 1 over sine.
Okay. And the bottom?
And then you do tangent into sine over cosine. And then you would do plus cosine over sine.
Okay. Now what's the next step? This is the key step.
You want to condense your the bottom of the fraction into one.
Yeah, you want to add those two fractions together in the denominator. Okay. Well, that means you're going to have a common denominator. What's the common denominator going to be?
Cosine times sine.
Yeah, I don't know why I prefer to write it like that, but I do. And what goes up over here?
On the top, wouldn't it be, because you have to multiply each by the, so it'd be sine squared plus cosine squared?
Yes. And what I always do when I'm adding fractions like that is, in fact, let me do it. I didn't do it here. I should have done it because it makes it a little easier to figure out. Draw 2 fraction bars in the middle. Put my common denominator there, and my plus sign there. Now, whatever I write over here, I check before doing anything else. Check, make sure this fraction is the same as that fraction. Okay. It's easy to do once you've done it like this. In other words, it's really easy to cross out a sine, and you end up with sine over cosine. So this one has to be the same. Okay, and then I get 1 over sine. And now I can draw that across, erase one of my common denominators, and now what?
Now you can use Python identities to get the top to be 1.
Okay. So I get 1 over sine divided by 1 over sine cosine. Now what?
Then you could like flip the second one and like multiply.
Flip and multiply, exactly. And what that gives you is cosine. Now, let's hope that's one of our options, and it is.
Yes, it is.
Okay. Okay. I'm not sure of a better way to do that. I did notice a section in my book right before we were going to go on today that confirming a non-identity, but it's just an exploration and they don't actually help you much with it. Oh, I see what they do. Yeah. Confirming a non-identity, the first step is graph both of them. Okay.
Oh, yeah, I have no idea.
So yeah, that's not going to be helpful to us. Let's take a look at the second one.
Okay.
Now, if we look at our possible answers here, I don't see any, there's a sign there, but it doesn't look like converting everything to sines and cosines will necessarily help. B is an interesting looking answer.
Yeah, it's really close.
I'll tell you why. If, let's see, if I'm not mistaken, I believe that that's the same thing as that. Okay, oddly enough. And the way you produce that is by multiplying by the conjugate, top and bottom.
Yeah.
And that produces sine squared in the top, and you end up with this. And so this identity, which looks a little odd, doesn't it? I mean, you wouldn't think that was an identity, but it is, and kind of get used to that one, because that will come up quite a bit. Well,
okay.
That looks a lot like B. Okay?
Yeah.
So I'm going to take the same approach. You know the approach I'm talking about? Where we
yeah.
In other
conjugates.
Yeah. In other words, my first step on this lower problem is I'm going to multiply top and bottom by the conjugate, and what that's going to produce is on the top I'm going to end up with 1 minus cosine squared, which is an identity that I can substitute sine squared for, and then that's going to take out one of those. So you end up with sine x over that. So I'm going to try to do the same thing here, I think.
Yeah.
Should work. We're going to end up with 1 minus secant squared. Yeah, that's a minus tangent squared. So let's try that.
Okay.
I'm not sure that there's instructions or a pattern or a method for always doing these when you have multiple choice.
No.
Just, I think it's kind of a little bit of creativity, trial and error, things like that. So, and one thing you don't ever want to do is multiply the tops together. In other words, leave it.
Oh, okay. Good to know.
If you multiply them together, it'll just make it harder. And what we have down here is that. And let's see, if our Pythagorean identity is this, then what is secant squared, or what is 1 minus secant squared equal to?
Negative tangent squared.
Yeah, so let's erase that, put negative tangent squared, and now that cancels with that. And I can take that negative sign. Ooh, hold on a second here. That's close to what we were looking at.
Yeah, it's just the negative.
So that must not be correct, huh? Yeah, no, that's not correct. B is not the answer.
Oh, they're trying to trick you, aren't they?
Huh? I guess they are. Let's look at this for a minute and see what else we can do with that answer. So if I start from there, there's a 1 plus secant x. Okay, here we're getting there. we got a 1 plus secant x in the numerator. That's that. And minus tangent of x, if you put that in the numerator instead of the denominator, it becomes minus cotangent x.
Oh. Wait, how do you get it to the numerator? I don't
Just make it 1 over cotangent x and then flip and multiply.
Oh, okay, yep.
Okay, and that answer is A. Again, it's...
With A.
Well, yeah, again, it's, I mean, I've been doing this for a long time, so it was kind of easy for me to try this one, to use the technique of the conjugate. But you know what? That's not that rare. In other words, whenever you see expressions like this, like this, like this, like this, think multiply by the conjugate, because what you end up with is 1 minus cosine squared, which can be turned into sine in both, or 1 minus sine squared, which can be turned into cosine. And the same thing applies when you're looking at things like 1 plus secant. In other words, if you multiply by the conjugate, you end up with 1 minus secant squared, which you can substitute minus tangent squared for that. So anytime you see a 1 plus a trig function or a 1 minus a trig function, or even if I saw secant x plus 1, if I multiply that, I get secant squared minus 1 once I multiply it by the conjugate, and that's tangent squared.
Yeah.
Okay, so very common technique whenever you see that. So the instant we see that 1 minus secant x, we want to be thinking along those lines.
Okay.
Okay. All right. Solving trig equations. That's actually much easier and a lot more fun. Yeah, I'd be amazed if you get more than one of these on a test. This is a practice quiz and he gives you 2 of them? Wow. Because these can take all day if you don't, I mean, these can be just terrifically difficult. Because you don't, you know, in a normal verify situation where you have what's on the other side, that gives you a direction to go. Whereas these, you're almost blind. You just almost have to start manipulating it and see if it takes you anywhere close to any of these answers. Because the alternative would be to take this and try to prove that it's not equal to A. Or it's not equal to B, or that it's not equal to C. And I'm sure that it's not equal to any of those. But how you disprove an identity is a whole nother matter. It's much harder than proving it. All right, let's look at this equation down here.
Okay.
Very typical. Most typical, now I said before that trig identities had no practical value in the world.
Yeah.
Other than teaching you your identities. Verifying trig identities, that is. Solving trig equations is a whole nother matter. There are all kinds of real world problems that result in trig equations. And so this is something you might run into if you're working in an engineering field or a technical field. Okay?
Yeah, okay.
These usually come down to quadratics or things that look like quadratics. This looks like a cubic. What can I factor out of that?
Factor out 2 or sine squared of x.
What's left?
2 sine of x plus 1 equals 0.
And now solve it just like you would solve any quadratic. You're going to set that equal to 0 and solve, or you're going to set that equal to 0 and solve.
Okay.
So let's set the first one equal to 0. It can only be equal to 0 if sine x is equal to 0. Where does that happen in this domain, 0 to 2 pi? Here we don't need the multiple choices. You want to be able to do this problem without multiple choice and then pick it from the answer.
Okay. So sine is 0 at 0 radians, right?
Yeah, the best way to answer this problem is not to look it up in your book. That's a terrible way. Try to draw the sine curve on your own from memory.
Mm-hmm.
That's how you
Okay.
answer it, okay? What two spots is sine equal to 0?
Oh, at 0 and 2 pi.
0 and pi.
Oh.
2 pi, incidentally,
Yeah.
is not in the domain. Notice the parentheses there. So 2 pi cannot be an answer, okay? But certainly
Oh.
0 and pi, sine x is equal to 0, okay? Now,
Mm-hmm.
solve the other half of it. Where is 2 sine x equal to minus 1, which means sine x equals minus 1/2. Where does that happen?
Wait, how would you graph that one? Or like how you did the other sketch?
We're not going to use that graph for this. And I'll tell you why.
Oh,
This is not going to be a quadrangle. You know what the quadrangle means? It's multiples of 90.
yeah, okay.
So whenever I have, if I want to solve this or this, I'm going to use my graph, my knowledge of the graph, because it's
Yeah.
those graphs that let you do the quadrangles.
Mm-hmm.
If you're doing angles other than quadrangles, you don't want to use the graph, you want to use those two triangles. And your knowledge of the unit circle. Okay, this is 3060. That's 1, square root of 3, 2. This is the 4545. That's 1, 1, square root of 2. Now you can solve this problem. First of all, what angle would the sine of x equal 1/2?
Would it be 30?
Correct, which is what in radians?
Is it pi over 5?
6. Remember that this number always multiplies to 180.
Oh, okay.
That's how you do a quick conversion from degrees
Mm-hmm.
to radians. It's pi over 6. It's pi over 3 would be 60 degrees. Pi over
Gotcha.
4 would be 45 degrees. Notice that those two numbers always multiply to 180, as long as it's just pi in the numerator. If I want to know if pi over 3 is 60, well then 2 pi over 3 must be 120, right?
Yeah, okay.
Okay, that's a good way to do it, is to know your pi over 3, pi over 4, and pi over 6 are, and then when you get something a little more complicated, just do it. So we know that it's pi over 6, but it's negative. What quadrants is sine negative in?
It's 3 and 4.
Okay, what's the equivalent third quadrant angle for 30 degrees?
210?
Correct. And then 210 is 7 pi over 6's, right? 210 is 7 30 degreesers, and so it's got to be 7 pi over 6 is the third quadrant one. And what's the fourth quadrant one?
So the angle would be 330.
Correct.
So is it 11 pi over 6?
Yeah, see how it's much easier converting between radians if you do it this way, as opposed to always using that pi over 180 conversion factor.
Yeah.
You get used to doing it this way, and you can do it pretty easily whenever you're working with these multiples of 30, 45, or 60. So, what's our answer?
Is it C?
Yeah. In fact, we could have almost, no, we had to go through, we had to pretty much be able to distinguish between C and D. I suppose had they only put 1 0, in other words, if D didn't have a 0 in it, then we wouldn't need to fully solve the problem, because once we found out that 0 was a solution, we'd know that that was the answer. But you want to be able to solve these anyway. This is solving a trig equation, and you don't want to have to depend on multiple choice.
Are the answers in C, are they in order?
Actually, not. That is a little weird. Why did they put it like that? That's kind of weird. They didn't even put it in numerical order. In other words, pi is less than 7 pi over 6. It's a bit bizarre, the order that they put it in.
Yeah, I know. I saw that too, but
everything else is in order. Even D starts with 0, and then pi over 2, and then pi, and then 4 pi over 3. Each one gets bigger, but C is a little weird. Yeah. I think that's probably just accidental.
Yeah, okay. Okay.
All right, simplify. Hold on. Surprised they only gave you one trig equation to solve.
Yeah, I think there's more because we have a second page, so.
Yeah. I mean, those, you would get a lot of those on a test, I would think.
Yeah.
Let's simplify. This is the same as question 1 and 2, is it not? Yeah. Yeah, exactly the same. Okay. So they just stuck a trig equation in there out of order, kind of. All right, let's see what we got here. All of our answers are pretty much in terms of not sine and cosine. So I would not start this problem by converting everything to sine and cosine. I suppose I might end up with D. Although, no, I won't say that. The convention is to never have the trig function in the denominator. In other words, this should always be converted to secant, rather. D?
Yeah. Yeah.
So I'm tempted to rule that out just because of that, but let's see, what can we do here? C looks like a potential answer.
Yeah, I would agree with that too.
Let me think for a minute. If I multiply by the conjugate in the denominator, I'm going to end up with cosecant squared minus cotangent squared, and I think that's minus 1. Is it not?
Yeah.
Okay, so let's do that.
Okay.
Hold on a minute. Sound like you have a little bit of a cold. Or allergies?
Yeah. Yeah, just a little cold.
I have allergies at this time of year.
Yeah.
Just wake up with. Okay, let's see. What's that give us? Again, never make the mistake of multiplying the top.
Okay, yeah, that's good to know.
I mean, we might run into a problem where we would have to do that, but okay. And this is going to turn into cosecant squared minus cotangent squared, which is negative 1, correct? Because cosecant squared plus 1 equal, or cotangent squared plus 1 equals cosecant squared. So yeah, that minus cotangent would be, oh, plus 1, not minus 1.
Wait. Oh yeah, okay, okay. I see.
Okay, because we're going to end up with cosecant squared minus cotangent squared.
Yeah, I need to leave the one, yeah.
Yeah, so it's plus 1. And now, is that
Oh, I see the line.
that answer that we were looking at?
Yeah, I think so.
They, no, right after I say never distribute it, they distribute it for this problem.
Yeah, I know, I saw that.
Hold on, they've got plus.
Oh, and we have a negative.
We got
Shoot.
negative. Negative is correct because I had to multiply it by their conjugate. So that's not going to be the answer.
Oh dear.
Yeah. What else? Wow. Ah. Ah. If we do distribute it, we notice something.
Yeah.
Notice that whenever you can get tangent times cotangent, that's tangent squared. Or
It is?
excuse me, that's 1. Okay? In other words,
Oh,
yeah, tangent x cosecant x minus tangent x cotangent x, that's 1, because that's tangent over tangent.
yeah.
So we end up with tangent x cosecant x minus 1 and cosecant x. I'll bet that word. I'll bet it's A. Let's see. Tangent is sine over cosine. Cosecant is 1 over sine. Sine's
Yeah, so
1 over cosine, which is C.
we can
A.
A. Jeez. Whew.
Okay, I see a pattern here. The pattern is they like to give you this answer here that looks very close to what you come up with.
Yeah, and then it's
Off
not
by
that.
a sign. I mean, it's off by a plus or minus sign. Well, instead of going all the way back and starting from the beginning, it's easier to take this answer that we came up with that had a negative sign and go from there. And we've seen it twice already, where you can get from what looked like it might have been the answer to the answer by working with the thing, by working with C, or by working with what we came up with and trying to prove C. That's what
Okay, yeah.
yeah, it's a little strange, but that doesn't seem to be a bad strategy.
No, not at all.
All right, let's look at 5.
Okay.
1 over secant x plus 1 over secant x minus 1. It's the very first thing you would just automatically do here if you weren't looking at any answers or trying to do anything else.
You want to condense it to one term.
Okay. What's the denominator going to be?
Secant x plus 1 times secant x minus 1.
Learn to put those two together quickly.
Okay.
Especially for trig. It's not a bad thing to do for algebra also. If I told you x minus 1 times x plus 1, you shouldn't have to FOIL that out. That's automatically going to be difference of perfect squares.
Yeah, x squared minus 1, yeah.
Same thing with trig, only in trig, it's much better to get difference of perfect squares, so you're always doing it. So this becomes secant squared x minus 1.
Okay.
And I did exactly what I said you shouldn't do, which was multiply them together too soon. It's nice to know that it's going to turn into that. But in terms of figuring out what our numerator should be, it's better to do this, and it's better to leave that line broken like this. Because now it's easier to figure out what should go over here. That's got to be secant x plus 1, right? In other words, oops, excuse me, sorry. Secant x minus 1. In other words, I need to be able to look at that and make sure instantly that it's the same as what I started with. That's just the left fraction.
Mm-hmm.
Because I can see that I can cancel that, and I'm left with 1 over secant x plus 1. Okay?
Mm-hmm.
I mean, this has to be the secant x minus 1, or plus 1. Okay? Now, let me just point out something here that not always obvious to people. As long as this is a plus sign, then I don't need to worry about parentheses.
Okay.
If that's a minus sign, then I do. I need to put parentheses around that, because if that were a minus sign, that minus sign would have to be applied to both terms.
Yeah.
And it didn't start out with parentheses. So if I didn't add them, I'm going to make a mistake. In other words, if that was a minus, and this is not just for trig, but algebra too. If that was a minus sign and I don't put the parentheses around it, those ones are going to cancel, and they shouldn't. I should end up with minus 2 when I put the parentheses around it. Okay? But as long as it's a plus, we don't need parentheses. Now, what's the new numerator?
Secant squared of x.
Not squared. We're adding a secant x plus another secant x.
Oh, okay. So it'd be 2 secant x minus.
Without the ones.
Do they cancel?
They do. Now, let's look at some of their answers. We know the bottom turns in, if I leave the bottom factored, do I see anything there that looks like this? I see a 2 cosecant x. I think I better turn the bottom into one term. It's going to turn into secant squared minus 1, and secant squared minus 1 turns into tangent squared. So now we're looking at this, correct?
Mm-hmm.
Now I notice some of my answers have sines and cosines in them.
So should we change them?
Yeah, I would change these into sines and cosines. It's looking like well, no, there's a lot of 2's there. In fact, every answer has a 2. I would change it into sines and cosines just to see what it looks like and see if it matches some of my answers that have sines and cosines in them. So I've got 2 over, this is the new numerator, secant is cosine, all over sine squared over cosine squared. You with me?
Why'd you put the 2 on top of the cosine?
Because secant x is 1 over cosine?
Yeah, I know that.
Okay, so let's...
so then
the 2 doesn't go with that denominator. In other words, what I have is 2 times 1 over cosine x. Okay.
Yeah, then you go.
Now I multiply numerators and I get the 2. Okay. Now I can flip and multiply. So we're going to multiply this thing by cosine squared over sine squared. And now I can cancel some stuff out. Cancel that with that. So now I have 2 cosine over sine squared.
And that can be changed.
Again, they do it to us.
Wait, where?
They give us an answer that looks very similar to that, D.
Oh, yeah. So would you
Ah,
substitute?
see, now I'm seeing what's going to happen here. Notice that cosine over sine is cotangent.
Yeah.
Okay, so I can pull a cotangent out of there in the numerator, and I'm going to have 2 cotangent over sine, right? In other words, if I here, let me scroll down a little bit. Just I don't want to leave you confused here. We have 2 cosine over sine times sine. That is cotangent.
Okay, yeah.
So now I have that. Okay?
Yeah. Okay.
And look at answer 2. That's very close. I've got 2 cotangent. Cosecant is 1 over sine. So that thing goes to this. 2 cotangent x cosecant x. Okay?
Oh, yeah, because you do.
Yeah. And again, haven't noticed if this is the case in all of them, but I would tend to be reluctant to pick that as an answer because I'm always going to put that as cosecant in the numerator. I'm never going to leave a trig function in the denominator. Same with a. That's always going to be secant to the 4th in the numerator.
Okay.
Now, I can't guarantee you that all of these will be like that. In other words, on number, let's see, number 1 was everything was in the numerator. Number 2, remember we didn't end up with this answer. We ended up with, I can't remember.
A.
A?
Okay. It was A.
And everything's in the numerator. So that's a little bit of a clue, maybe. And same thing on 4. We didn't end up with D. We ended up with B, if I remember right.
It was A.
A, yeah, okay. And same thing with number 5. It appears all the answers are going to be in traditional, acceptable math format.
Yeah.
It's like that. You don't put an I'm trying to figure out why this is the case. Why is math format you do not put an irrational number in the denominator? Why is that?
Is it?
I mean, this is just curiosity between you and me. My thoughts have always been, well, you can't actually divide something up into a number of pieces if you don't know what that number of pieces is.
Yeah.
Okay. But I certainly have seen pi in the denominator of many of the answers, and that cannot be rationalized. You cannot rationalize it when you have pi in the denominator. So this is acceptable because it's the only way to write it. But this is not. Well, I guess a similar thing might apply to trig functions. I don't know. I would say that if you're looking at something that has the trig function in the denominator, I would try changing it. In other words, this answer D over here should be 1 minus secant x.
Yeah, I see that. Okay.
All right, let's see. We need to go to another page. You need to send me another page?
Yeah, I'll do that real quick.
Okay. Yeah, once you've done it once, the second one is going to go faster. Oh, you sent it already. Sorry.
Oh, no, I didn't. I sent the first page twice on accident.
Oh, okay. Oh, and I didn't get it right away. You sent it again. Yeah. So I think that's more of a function of the internet and Google, Gmail and stuff as to how fast I get it or slow.
Yeah, probably. Okay, I just sent it.
All right. We'll see how fast it gets here. Pretty fast. That wasn't bad. It was only like 5 seconds. Whoops. I realized I can't do it that way. It doesn't allow me to rotate it unless I download that file and pull it up like this. and then I can write. Start at the top. We got 15 minutes. You tell me. We probably won't be able to cover the whole page, so if you're a little unsure as to some of these,
can we do?
We better do this one because it's got a pi over 2 minus x.
Okay, and then can we do 9 after that?
Yeah.
Okay.
Whenever you're looking at pi over 2 minus x, you're looking at the co-function.
Yep.
So we know what our very first step is going to be.
You have to change that into sine of x.
Yeah. Okay, and secant is 1 over cosine. So we'd have sine over cosine. Tangent, is that on there? It is.
Oh yeah, it is.
And the other general rule is if you have two terms that you can turn into one term, always do it.
Okay.
Okay. Number 9.
That one was fast.
Yeah, that didn't take long. We'll do 9 and then we can go back to 7 and 8 if we still have time.
Okay.
Okay, 9 is basically a quadratic.
Yeah, it's just not, yeah, it is.
Let's talk about that for a minute. If I said x to the 4th plus 2x squared y squared plus y to the 4th, that's got to be x squared plus y squared squared. See why?
Okay, yeah.
In other words, this fits the pattern of what you get when you take a plus b squared. When I take a plus, and this is something else you want to memorize. You don't want to have to FOIL this to come up with the fact that it's always a squared plus 2ab plus b squared. Okay? Well, in this problem, or the other side of that is a minus b squared is always a squared minus 2ab plus b squared. Okay, so we're looking at this right here where a is secant squared x and b is tangent squared x.
Yeah.
So I know immediately that this has to be secant squared x minus tangent squared x all squared. What's secant squared x minus tangent squared x equal to?
Would equal to what? -1?
No. Look at your trig, write your trig identity out and then solve for secant squared minus tangent squared.
Okay.
That's always the best way to do it because it's easy to get the sign wrong on these.
Yeah.
Tangent squared plus 1 equals secant squared. Now subtract tangent squared from both sides. That's what it's equal to.
That's +1.
And then 1 squared is 1. So D.
What?
I'm sorry, what?
It's just 1 then? Okay. Can you just go over again, like, if I saw that and then, like, to factor it, like, because you kind of went over it, but, like, how would you do that? Because doesn't
the best thing to know how to do that is to know what this is.
Okay.
In other words, memorize this. Don't have to solve this every time by foiling. Because what you want to do is you want to be able to go backwards. In other words, if somebody gives you this expression, you want to know that that's a minus b squared. And it's hard to unfoil it. If you always have to foil it, you're going to not be able to recognize when you're looking at this side of it.
Okay, yeah.
Okay? So a question on a test once. What is this number? Even if you were allowed to use a calculator, this would be a hard thing to figure. But not if you recognize that as, gosh, that's got to be 100 minus 99
Squared.
1.
So it's 1. Yeah.
And yet, if you didn't know that, without a calculator, you'd have no shot, right? I don't know any.
No shot, yeah.
I mean, you probably could do the long, it would take you 5 minutes without a calculator.
Yeah.
Even with a calculator, it'd be real easy to make a mistake. So the best way to do this kind of problem is to recognize that that's 100 minus 99 squared. Okay? I don't know how else to solve that if you don't recognize. In other words, that's awfully hard to factor.
Yeah, it's very hard.
Just like this is a little difficult to factor if you didn't know what it was.
Yeah.
Okay. There's something called U substitution. Gosh. U substitution. What have I told you this? That is what I call a quadratic in disguise. Okay? The way I'm really going to do this is I'm going to let u equal the middle term. And now this whole thing converts to u squared minus u minus 2 equals 0. That fact.
We did these in Algebra 2.
What's that?
We did these in Algebra 2 last year. I remember this.
Yeah, this u substitution, you don't actually have to use it if you get to where you can recognize that's quadratic. But what ends up being my answer is e to the x minus 2 times e to the x plus 1. In other words, at the end, you go back and resubstitute.
Yeah, resubstitute.
It's a helpful concept merely to recognize that we're looking at a quadratic. Okay?
Yeah.
It's not a typical looking quadratic. Same thing when you have sines and cosines. In other words, I'm sorry we didn't get a chance to do a little easier one. Maybe we still have time. Let's see. Yeah, let's look at number 10. Well, no, that's not what I'm looking for. I'm looking for, no, that's just another verifying. Even 7 isn't quite what I'm looking for. I'm looking for something that looks like this. How would you factor that? And it's factorable because it is a quadratic. It's a quadratic in disguise. It's a quadratic in trig functions. It's called a quadratic in sine x. Just like the last one I showed you was called a quadratic in e to the x. Well, if you want, you can do the u substitution, makes it a little easier. Always let it equal that middle term.
So it would be negative 2 and 1.
And now resubstitute sine x. So
it would be sine x minus 2 and then sine x plus 1.
Correct. Now let's keep going. Let's solve this problem. This is a key problem here. I can't believe this isn't on your test. Your test preparation. There's a couple of things going on here. First of all, we had a quadratic in disguise that we factored. Now let's solve it.
So then you get sine x equals 2 and sine x equals negative 1.
Where is sine x equal to 2? Think of your graph.
The graph.
Look at your graph and see if there's any place on that graph where sine x is equal to 2. It's always between -1 and 1, correct?
Wait, what do you mean between -1 and 1?
If I draw the sine graph, its range is always -1 to 1.
Oh, yeah, okay.
Never 2.
So it's not a solution?
Exactly. Cross that out. Whenever you get the sine or the cosine of an angle equal to a number greater than 1, it's impossible.
Yeah.
Okay, so the only solution to my quadratic is that, and where is that true? What angle is the sine of that angle equal to -1?
So would you use triangles for that one?
That's a quadrangle. In other words, whenever your answer is 0 or 1 or infinity, it's going to be a quadrangle. And you're not going to be able to solve it with those triangles. But you can solve it here.
So would it be 270 degrees? So that would...
That's 2 pi, that's pi over 2, and that's 3 pi over 2.
3 pi over 2.
Those are key marks on the x-axis in radians. Those are always going to represent your highest point, your 0 point, your lowest point, and your back to the start point.
Okay.
So the answer would be 3 pi over 2. And that's it. There's only one spot in that first unit circle where sine of x is equal to -1. Okay? So that's why I tell everybody, always memorize your sine and cosine graphs so that you can instantly draw it from memory and then find out where all these key spots are.
Okay. And then before we finish, I just have like one quick question. So let's say it's one of the like quadrangles and it's at like 180 degrees, which is like the axis. And then it's something where like sine has to be, or like secant has to be negative, but like, so like the quadrant above it, like quadrant 2, it's negative there, but like quadrant 3, it's positive. So would you count that angle, like 180 degrees?
No. Quadrangles are not in any quadrant. Okay? So if you take your 6 trig functions of your 4 quadrangles, the answers are either going to be 0, 1, -1, infinity. In other words, if the sine is equal to 0, what is the cosecant equal to? At this point, right, here's the cosecant plotted on top of the sine. They both have to be 1 at the same point, right? There's a vertical asymptote there. So the quadrangle angle, in other words, the cosecant of pi is undefined.
Okay, yeah, that makes sense.
And the cosecant of 0 is undefined. It's always going to be undefined if its reciprocal is equal to 0, because that means you're going to be dividing by 0.
Which you can't do, yeah.
Right. And so there's a lot of vertical asymptotes in these trig functions. There's also vertical asymptotes with tangent. Tangent has vertical asymptotes at minus pi over 2 and at plus pi over 2 and every multiple of pi. In other words, at 3 pi over 2. Tangent looks like this. Whoops, I'm trying to draw where it's asymptotic with those asymptotes. So the tangent of pi over 2 is undefined. So all trig functions of all quadrangles are either going to be 0, 1, -1, or undefined. I can't think of another answer for any of them.
Okay. Thank
Okay,
you.
and you can't get those from your two triangles because there's no quadrangle in those two triangles. There's 30,
Yeah.
45, and 60. Although there is a technique for figuring out what that is, but I'll tell it to you next time or something. But
Okay, yeah. I don't even know because we use the table mostly, so.
yeah, and number 10 is pretty easy. You don't have to factor that. Just move the 1 to the other side, divide by 2, and then take the square root of both sides. The only
Yep.
thing make sure is that when you take this, whenever you solve any equation by taking the square root of both sides,
Plus or
begin your
minus.
answer with plus or minus.
Yeah, okay.
So
Perfect.
cosine of theta is going to be plus or minus the square root of 1/2. And that's going to give you 4 answers. I know what the answer is without doing the math. It's got to be D.
Yeah, gotta be D, yeah.
Okay? Because
That
there's
makes sense.
got to be 4 answers. And you know it as long as you get to the point where cosine of x equals plus or minus 1 over root 2. Well, there's 2 places where it's equal to plus, and there's 2 places it's equal to minus, so there's got to be 4 solutions.
Yeah, that makes sense. Okay. Perfect.
All right, Lauren.
Thank you so much.
You're welcome. You have a good week. I'll talk to you next time.
Perfect. Thank you.
Bye.